So let's start. So I will not thank the organizer for the invitation. I will thank the audience to attend this workshop. And of course, I would like to acknowledge all my collaborators, because I'm going to present you several results that have been made with various collaboration. We have a very nice consortium. I will not cite all the names, but roughly speaking, you have a mathematician and theoretician, the group of Gennadiel, Alex Tovbis, Andrei Gelash, Dmitry Agafontsev, people from hydrodynamics, so Eric Falcon and Nicolas Mordant in particular who gave the talk, and people from the École Centrale Nantes, Félicien Bonnefoy and Guillaume Ducrozet. And of course, people from optics and from our group, so Stéphane, who have seen the talk, and François Copy, who is here. Okay, the perspective of my talk will be the following. I will try to show you that as a physicist, the interest of soliton gas is not only the beauty of the concept, but it's also the fact that it can be very useful to understand at the theoretical level natural phenomena, okay? And I will focus on the so-called modulation instability, also called Benjamin Fair instability in hydrodynamics. And it's first seen as sideband instability, which is the fact that the homogeneous solution of the focusing nonlinear Schrödinger equation, so the plane wave, is unstable if you add some harmonic perturbation. Where is the laser? That's very nice to be an optical guy and do not find the laser. So if you put a harmonic perturbation like that, the perturbation will exponentially grow if the frequency of the perturbation enter within what is called the gain of modulation instability. So be careful for mathematician, because my variable of evolution in my experiment is the distance of propagation in optical fiber or in water tank. And so my conceptual space is the time, okay? My initial condition is that Z equals 0. So everything that you have in mind when I speak about experiments, my space is in second, okay? So my frequency, of course, conceptually, it's a wave number. And when you have that, it's well known that it leads to a breather solution of a nonlinear Schrödinger. And what I'm gonna look at is the following problem. Now we look at the spontaneous modulation instability. So we replace the harmonic perturbation with a random noise. And in this case, you can run numerical simulation of the focusing nonlinear Schrödinger equation. So you start from something which is the background, the condensate, okay, plane wave with some small noise, and you let it evolve. And what you see is the emergence of structures that locally, if you do some local IST, for example, you will see that locally most of these guys are genus 2 solution. Okay, so mainly people think about this problem as a problem of breathers. Okay, when you are in the community of photonics in particular. So this problem has been investigated extensively in this paper by Agafontsev and Zakharov. And the main important result is that at long-term evolution, you get a stationary state. Okay, so it's a fundamental example of integrable turbulence. You have an integrable system, which is focusing NLS. You start from random waves, and at long-term evolution, you have a stationary state in the statistical sense, okay? So you can characterize it by several statistical quantity, such as the Fourier spectrum. So the stationary Fourier spectrum has this peculiar shape. Here, this is a signature of this modulation instability gain, and you have this exponential tail in the Fourier spectrum. You can look also, for example, at the nonlinear part and linear part of the Hamiltonian, and you have an oscillatory regime in the transient regime that is not fully understood yet today theoretically, but in the long-term evolution, you have a ratio 2 between the nonlinear part and the linear part as a kind of virial theorem, if you want. And moreover, if you look at a single point statistics of the modulus square of psi, which is the intensity in optics, okay, the optical intensity, you get an exponential law, which corresponds, Stefan told you, to a Gaussian statistics for the real part and the imaginary part of psi. So as if it was linear superposition of wave. And of course, it's not. It's nonlinear state, okay? And more recently, we have shown that if you now look at 2 points correlator, okay, so you look at correlation in intensity between 2 points, so in time for us, but in space for mathematician, okay, you end up with this very peculiar oscillatory structure of this G2 function, okay? If it was random ways, you would have something greater than 1 everywhere, something like that, okay? So this is really a strange structure. So the question up to very recently is there was no theoretical description of this phenomenon, which is very common and studied since 50 years or something like that. So the idea that I will show you is that, and Thibault in his talk also spoke about that you can use soliton gas to model modulation instability. So for that, we have to think about what does it mean for an experimentalist, a plane wave. Plane wave does not exist, okay? So plane wave for a mathematician, so plane wave, I'm speaking about the solution here, the homogeneous solution, okay? So this just equal to 1, okay? So for you, this can exist on a full line mathematically. But of course, experimentally, this does not exist. Whatever you do, what you need to do is you need to cut it, okay, somehow, because you have finite size. So what does it mean that it's a plane wave experimentally? It means that the effect due to the edge at the time that you are looking at your solution, so for example, I let it evolve at another time, I look at that. And the important thing is that the effect of the edge does not affect what I'm looking at in the central part, okay? And later in my talk, for technical reasons that I will not explain to you, I only look at that. So I have a very long pulse, very long is 30 nanoseconds in optics, okay? Very long pulse, and I'm only looking at 200 picoseconds. And I have no effect of the edge. So it means that conceptually, if I am at a finite time, so finite Z for me, I can probably model just by a box, the plane wave. So the good thing with that is that the eigenvalue of the box are known, okay? There are exact formula that give you the soliton content of the box. And in the semi-classical limit, so when the size of the box is very large, you can neglect the continuous part of the spectrum. So that was the idea, to connect the soliton gas with n soliton solution with the problem of the box, okay? So of course, it's connected to all the talk that we had about soliton gas, but here it's very specific because I will look at homogeneous and stationary soliton gas, so the density of state does not depend on anything, okay, in what I'm going to look at. So what do? We start from the known eigenvalue of the box. So here it's not the exact formula, it is the approximation, Bohr-Sommerfeld approximation, the semi-classical limit of the box. So you have this eigenvalues that lie only on the imaginary axis, so it's a bounce state, okay? And what do we want to do? We want to look at the evolution of that in the very long-term evolution. So there is something similar in wave turbulence when you want to do that. In wave turbulence, the good basis to think is the Fourier modes. And what you say in wave turbulence that at long-term evolution, you will have a stochastization of the phase of the Fourier modes. So it's natural to do the same here, to say, okay, we have this n soliton made with this eigenvalue, but the long-term evolution, just because of my initial small randomness, will transfer into random phase of the norming constant. So it's what we did with the procedure introduced by Galash a few years ago. We built the n soliton solution with these eigenvalues and random phase between 0 and 2 pi for the norming constant. Okay, so this is such an object with 100 of soliton. And now what we can do is to look at the statistics of this guy. So we can generate many of them, and we can also propagate this with an NLS solver. So this is the result that Thibault has shown you yesterday. So this is the numerical simulation starting from the plane wave, okay, in NLS solver, and you have what I've shown you, the modulation stability. And now here, it's the dynamical evolution of my n soliton build as I've shown you, okay? So already by eyes, you are quite happy. But of course, what we want to look at is quantitatively at the correspondence for the statistical variable. So the Fourier spectrum, you have in blue, in red, the difference. Do you see any difference between the Fourier spectrum of the and soliton solution that we have built and simulation of the plane wave in NLS. You don't see anything, okay? You can look at the single point statistics and you can look at the 2 points correlator, okay? So if what I don't show you that, but I can show you during the question if you want. If you change slightly the distribution of the eigenvalue that correspond, we understood after that, to the condensate that is in the paper of Gennady and the Weil condensate in the paper of Gennady and Alex. If you change a little bit the distribution of eigenvalues, you don't have such an agreement, okay? So it means that it is the correct soliton gas to model modulation instability. Okay, let's go to experiments. So we can have two kind of questions now from what I'm showing you. It's to do experiments, so in optical fiber, in water tank, to look at the statistical properties that I've shown you, okay, Fourier spectrum, statistics, and all that. So I will show you some experimental results about that, and look with the eyes of the soliton gas. So let's try to measure the density of state in real experiments to see this Weil distribution. Okay, the Weil distribution is this distribution for the density of state, which is the probability density function associated to these eigenvalues. Okay. Okay, so one thing that you probably all know, but when we speak about nonlinear Schrödinger equation, it's an equation that describes the envelope of the field. What is very nice to notice is that the carrier wave is very different for the time scale in optics, which is the femtosecond, and in water tank, in which it's the second, okay? The time scale of course of the structure, so the solitons are typically the picosecond in some of the experiments I'm going to show you in optical fibers, where of course it's a few seconds in a water tank. But interestingly, the length of propagation that you need to have the same nonlinear effect, it's quite similar. It's hundreds of meters, okay? Okay, so this Stefan has shown you. So it is the modulation instability. As I've drawn here, the plane wave is just a very large box, okay? And in the middle, you see the emergence of the so-called modulation instability that has been observed many times. So, but now we look with the eyes of statistical properties that I've told you. So we analyze the data. It's something that we have done with the consortium I've told you. So you see here the evolution during the propagation in the water tank of the 2-point correlation by G2 function. And you see that after some propagation, you have these oscillatory structures that I've shown you. And you can look at the kurtosis, which is proportional to the nonlinear part of the Hamiltonian of the nonlinear Schrödinger equation. And you see that we start to observe this oscillation, okay? We can do the same thing in optical fibers. So modulation instability in optical fibers, we are speaking about 1,000 of paper, okay? It has been studied a lot since this first paper, in which the observation was only the average Fourier spectrum, okay? And it's only recently that it's possible in optical fiber to observe the dynamics in single shot of this very fast time scale. So in our lab, we have developed two different setups. One has been introduced by Stefan quickly. I will not go into detail, but the idea is that this large box propagates in a loop of fiber like that. So it means that you can extract the information at different distance of propagation equivalently, okay? And then you can reconstruct what happened in time here, which is our conceptual space, as a function of the distance of propagation. So this is the first experimental observation in optics of the spatio-temporal spontaneous modulation instability. And with this setup, we don't have access to the phase, so we cannot measure the density of state. Okay. With other setup, we can measure phase and amplitude with this fastest time scale. So we have developed a very specific thing to be able to record sub-picosecond time scale amplitude, so intensity and phase with sub-picosecond resolution. And with all this, we can look at the transient regime that I've shown you about the statistical variable. We can look at the convergence toward the stationary exponential PDF, and we can look at the emergence of this oscillatory G2 function. But so here it's you average, okay? Because here you are looking at the statistics, the probability density function of this guy. Here it's autocorrelation. Yeah, so just my next slide. It is here. So now here, this is the input of my fiber. It's an example. So I told you it's a small window of observation, but the experiment is actually much larger. Okay, it is technically I cannot observe more than that. So you have the initially the condensate with some small noise and the phase with some small noise. Okay, so now I can compute the IST spectrum of this guy. Of course, conceptually, I would like to have infinite line. I don't have it. Okay, so I have discrete point because the observation is on a box. Okay, so here you see just the points of the formula that I have shown you is just to show that you have a nice correspondence. Not surprising because I am just showing you a box with some small noise. But what is important for a physicist is not to do physics, so we'll propagate that in the fiber, okay, in the real world. And if it was just NLS, it means that the spectrum should not change. And oops. Does it work? So if it was integrable system, the IST spectrum would be a constant, and it's not. So this is after strong propagation in the fiber. So of course now I have, because of modulation instability, I don't see at all the plane wave. Okay, this is evolution of the phase of intensity, and these are the discrete point in green that I can measure. Interestingly, if I look now at the statistics of the density of state, which is the statistics of this guy divided by the length of my recording, I'm still quite close to the Weil distribution. Okay, so for the imaginary part, it's not perturbed a lot. And actually, there is a lot of physics in that. So let's look at the density of state in the experiment in 2D now, okay? And let's compare that, not to NLS, but to a generalized nonlinear Schrödinger equation that describe experiments in the fiber. And in particular, by introducing the Raman scattering here that plays a crucial role. And you see that in 2D, what you observe in simulation, and you observe it in experiments, is that some of the real part goes to the right and some of the real part go to the left here, okay? So one of the important questions that we have now is to add to Soliton gas theory some adiabatic change, some adiabatic breaking of integrability to look at this, okay? And I will not go into detail, but this is related to what is called the rate shift induced by Raman scattering.
Do you have a sense of whether dispersion or Raman effect is more responsible?
Yes, if you don't mind, I go to the end of my talk and I have a slide with all the details. So just to quickly, I will go back to the stimulated modulation instability. So forget about the noise. I speak again about just harmonic perturbation. Okay, so it has been studied a lot, and in particular by Constant Stauber that has shown. I gave a talk at the beginning of the week, and many papers after that. And what is known, if you look at that with the eyes of the finite gap theory, is that the main branch cut will have open gap due to the harmonic perturbation. And the nice result is that the specific point of the branch cut that is going to be opened is related to a given Fourier modes. Okay, so one unstable modes correspond to one opening of the gap. And there is a formula that gives you, in the perturbation theory, that gives you the direction of how the gap are open. Okay, so we have started this preliminary experimental result. We have started to look at that in experiments. Okay, so what we do is we put only one perturbation. Okay, so I don't have the negative frequency, only one. Okay. So these are the experimental results. So you have the plane wave with the modulation, okay, and you have some modulation of the phase. And these are the IST spectrum that we compute from that, and the red cross are the theoretical curve for the opening of the gap, okay? And again, what you see, this is the initial condition, you propagate a little bit, not that much, you see, it's not a big perturbation, just the beginning of the increasing of the perturbation, and you see that because of high order effect, you have some change, okay? And this is just another example with a different strength of the perturbation. Let's conclude to have some time to discuss maybe. So I've shown you, I hope to convince you that soliton gas can be used to model natural phenomenon. Okay, I've taken the example of modulation instability, and it is only the beginning of the story, because modulation instability is described by a bond state soliton gas, homogeneous soliton gas. But of course, we can think about many different things. Inhomogeneous physics, random waves that are much complicated as just a plane wave with some small additional noise. Okay, so I think it is the beginning of the story. I have an important question for myself, which is, okay, we describe this modulation instability with soliton gas, but we want to speak about genus 2 solution when we speak about modulation instability. So is it possible statistically to describe that with a breather gas? We don't know, but it's something that we are thinking about. And I can add a third way of looking at that, which is related to the work of Gino, which is if you have non-zero boundary condition and you put some perturbation locally with a given size L, is it possible in a certain limit of L going to infinity to reach also the same statistics? Okay, so I think that there are many questions about that. Of course, I told you one of the important things for me is, can we think about, and maybe generalized hydrodynamics can give something about kinetic equation, including breaking of integrability. And finally, of course, we have Thibault has shown you that the kurtosis of the modulation instability can be computed with the soliton gas, but what we want to have is all the statistical variables. So let's dream about having the Fourier spectrum from the soliton gas theory, the full PDF from the soliton gas theory. So all the variable in the physical space, not in the IST plane. Thank you very much.
Thank you, Pierre. Questions?
Maybe I can go to the question of Gino
Yeah,
about the
Mhm.
Raman.
Mhm.
So these are the different more detail. Okay. So this is the influence of the third order dispersion, and this is the influence of the Raman scattering. So you see that what does this kind of snake shape is the Raman scattering. So personally, it would be what I would look at at first as importance.
I think we might have a question by Tamara.
Yes, I have a question. Okay. Hi, Pierre.
Hello.
Thank you very much. Now, I would like to know, you have the 2-point function, you show a certain point, the 2-point function. Do you know what is the shape and how it behaves for a long time? So for a long space in your case, no? I mean, so...
I'm not sure to understand. What do you mean?
No, what is the behavior for, so this is
it goes toward this one where, sorry, where is it? Do you see my slide? Sorry, pop up. No, it was before. Yes, it goes to this one. So this is it's a stationary 2 points correlator.
So it doesn't change with, I mean, with time for me, no? I would be so.
Yeah, exactly. It doesn't change with time. Exactly.
It doesn't change. Oh, it's okay, surprising. But
it is surprising.
Yeah, very surprising. Can you show me the picture below where it changed? So what does it change then?
So
yeah.
here it's because it's experiments. Yeah, I'm speaking.
And this one, yeah.
Yeah, so here it's why it changed. It changed because it's experiments. So in experiments, you have also some damping, you have some other effects. So here it's not purely integrable. Okay. If you look at the numerical simulation, you will end up with these oscillatory structures in a stationary manner.
I will be stationary, but for this particular, so just to understand, the particular choice is the spectrum, which are things by law, and the random.
Exactly. For this one, it is
uniform
stationary.
variable. Okay.
Exactly. So the key point is random phase of the norming constant. Exactly.
Okay. Thank you. Thank you.
Any more questions for Pierre? Yeah.
Yeah, also about this 2-point function, if I subtract, I mean, without the correction, just the integrable case, if I subtract 1 and integrate over your time or my space, I get 0. Is that correct?
Yeah, I think yes, probably.
And is there?
I can check that, but yes, I would say yes.
You have a good reason for that, or
I don't know. It's, you see, in quantum mechanics, it's benching, anti-benching at the same time. It's very strange. But it's a signature. I mean, the physical, it's a it's a physical signature of the fact that you have this time scale of the modulation instability. Okay, so you have a breather-like structure that go to 0 and that remains statistically. Okay, so it's a signature of that. It's a statistical signature of the breather.
Yeah. So it's the condensate effect essentially. Is that correct?
Yes, something like that.
Yeah. I have a quick question, actually. So when you do the measurement, you said that you're measuring in a smaller box compared to the signal. So if the time evolves, then the content of solitons in that box will also change, because there will be solitons coming from the left and soliton going out of the right.
So generally speaking,
so why do you compare the two spectra?
So generally speaking, it's completely true. But here I'm looking at modulation instability that is modeled by bound state. So solitons do not have any velocities, okay? And then I have looked at density of states. So I'm doing running many experiments and computing the average.
On the statistics, okay, makes sense.
So it's two things in my talk.
Thank you, Pierre. Well, if there are no other questions, let's thank Pierre again.